Hello everyone, this is the basic Georgia Tech Solar Racing 3D FEA tutorial, and we are going to be using our hub for SJ1 as our demo part today, and we're going to be using a 2G bump load on it. So that's what we're going to be testing, and let's get to it. First thing I've done is I've gone ahead and opened the part in SolidWorks, because that's where I've created the part. Unfortunately, our FEA software doesn't take in solid parts, so what I'm going to do is I'm going to hit Save As. I'm going to, instead saving it as a part, I'm going to save it as a parasolid, the .x_t file. Make sure you don't save it as a parasolid binary, it's got to be a parasolid. And go ahead and click Save. Now that I've saved the file, I'm going to open up NX, which is the FEA software that we use. And if this is the first time you're opening up NX, you might need to go to File, Utilities, Select Bundles, and make sure you've added ACD 30 and 31 bundles to your selected bundles. Otherwise, you're not going to have the tools you need to make this work. But we have already done that. This is not the first time NX has been opened up on this computer. So I'm going to go ahead and click New. And I'm going to make sure Model is selected under Model tab. And I am modeling our hub, not our wheel, our hub. And make sure you change the folder. You don't want to use this folder. Instead, you want to use whatever folder you've created. I've made a nice one called FEA Training. It's perfect. You'll want to make one folder for every FEA you do, because FEA generates a lot of files. So you want those to be all stored in one nice location. So go ahead and click OK and OK to create your model. Now, NX is also a wonderful CAD software. We don't use it for CAD, but it does exist as a CAD software. So actually, I could create the wheel feature by feature in this window, but instead, I'm just going to import it straight from the file we've created. So File, Import Parasolid, and click on the hub and click OK. That nice little parasolid file we've created, and here is our hub imported into NX in the same orientation as it was in SolidWorks. So, first thing I'm going to do, now that I have my parasolid imported, is I'm going to go ahead and start my advanced simulation. So hit File, Advanced Simulation, and here it's been created, and hit click New FEM and Simulation right up top. This is going to create a finite element model and a simulation file, and the only thing you have to change in this dialog window that's popped up here is the geometry options. Make sure you click All On, OK, and OK. I'm going to title this my bump load, because that's what I'm going to be modeling today. I'm going to be modeling the hub under bump loading scenario. I don't have to mess with any of this stuff because I am actually going to be using the most basic of simulations. I'm going to be using Nastran Solver, which is industry standard, a great solver. I think it was originally made by NASA, I'm not sure. It's going to be a structural analysis. You can also do thermal analysis, but we don't do a whole lot of that on this team, at least on the mechanical side. And then we are going to be using the most basic linear statics solver. Later, when we get the more advanced FEA, we'll work with some of the more stuff down here, using case control to override errors and bulk data if we need to import. Loading scenarios from other programs. But for the time being, this will work just fine for us. All of their built-in tools are just perfect, so we'll go ahead and click OK. And now I've created my FEM and SIM files. The first thing I need to do after creating FEM and SIM is mesh my part. I need to take this part, which is just a bunch of geometries right now, and turn it into tens of thousands of individual nodes and elements. So what I'm going to do that, because it's a rather complex part, I'm going to be using a 3D tetrahedral mesh. Go ahead and click that button. First thing I'm going to do is select my body, which is going to be this guy. Notice if I mouse over it, the entire thing turns red. That means I'm hovering. And if I click it to select it, it turns gold because it's selected. Next thing I need to change is the type. I am not going to be using usually you guys are not going to be using C-tetra 4. Usually you'll be using C-tetra 10. It uses more nodes with the same amount of elements, and it's a little bit more accurate. But for today's model, I'm just going to stick with C-tetra 4 because it's faster. And in order to figure out my element size, this is where some engineering has to be done. I'm going to go ahead and open up SolidWorks again, and use the Evaluate Measure tool. And this is going to allow me to measure what the smallest feature on my part is that I'm worried about. The smallest feature I'm worried about looks like this wall thickness here. So whatever this wall thickness is, that's going to be my smallest element. I'm going to click on that guy and that guy, and I'm going to give you the distance between them. It looks like 4.8 millimeters. So thank you very much, SolidWorks. I'm going to go back to NX and change this. I usually like to do whatever my smallest feature is. I want to break that down into 2 elements. So I do 2 millimeters here normally, but to speed things up, I'm going to make them 4 millimeters as my average element size. And what that's going to do is it's going to set the average size of my element size. The distance between 2 nodes is going to be 4 millimeters. The last thing I need to do in this dialog box is change my destination collector. This is going to define my material properties for this mesh. I don't want to automatically create one. Instead, I'm going to create my own. So I'm going to hit New Collector. And my collector, because we make our hubs out of aluminum, is going to be aluminum. And so I've titled it aluminum. I'm going to create a new physical property. I'm going to call this aluminum. And instead of inheriting the material property, because what that would do is look back at the NX model, but since we modeled it in SolidWorks, it's not going to know what to do, so I'm going to choose my own material. I'm going to click Aluminum 6061, because that's what we're using. We have a lot of different materials for you to select here. Oftentimes, we'll also be using steel. That's a thing to look for. And our wheels are made out of magnesium, which they also have right there. But today, we will be using aluminum. And if you're using a new material that they don't have in here, if they don't have the material specs that you want, you'll go ahead and create a new material, but we won't be doing that today. So just click OK, and OK again, and OK again, and now we have created and selected our aluminum destination collector. That's the last thing we need to do in the mesh creation, so I'm going to click OK. This process is going to take a little while. Basically, what it's doing is it's filling up all of those geometries with tens of thousands of little 3D tetrahedral elements. And the way it does that is first it completely fills the part with little nodes, little points called nodes. Those are the things that are spaced about 4 millimeters apart. And then it fills in those nodes with tetrahedrons. And that way it can use just a giant differential equation solver after we apply our loads to work with the rest of it. And guys, normally that process is going to take a little bit longer, especially if you're using your laptop or connecting via remote desktop connection. And one more thing to worry about for you guys doing that, if you aren't using a nice fancy computer like this one, is if you mouse over the part, you'll notice your graphics card is going to have a really hard time, even if you just like breeze over it on accident. Every time it selects this thing, it's going to individually select every node, and then individually select every connection between every node, and then individually select every element. And then when you mouse over, it's going to undo all of that in backwards order. And it does that element by element. So for those of you with slower graphics cards or connecting via remote desktop, that's going to be very difficult. And so try to avoid doing that because it's just going to be a frustration. So now that I've created my 3D tetrahedral mesh, I'm going to go ahead and start applying aspects of my simulation. So actually simulating the loads and constraints this thing is going to feel. So how I'm going to do that is by clicking Activate Simulation right up here. And now I've activated my simulation file, which means I can start constraining and adding loads. So first thing I'm going to do is constrain my part. And I have a lot of constraints to pick from. This honestly takes a lot of good engineering, intuition, and knowledge as to how to do this. There's a lot of different ways to constrain a part, and there's a lot of good theory that goes into that. So, example being, if you have a part that is on a slider, so something that would slide back and forth on maybe a linear bearing, the degrees of freedom that you'd want to remove are different than those if you are bolting something down, right? So So there's a lot of different good choices here, and they all do something else, and they all remove their own degrees of freedom. And if you prefer to pick your own degrees of freedom to remove, you can just click user-defined constraint. But for us, we're going to be doing a full fixed constraint because that's how we treat our bolt holes on the edges of this part. So I'm going to click fixed constraint, and I'm going to fix in space. I'm going to say these points are not allowed to move at all. So how I'm going to do, so how I decide which points are not allowed to move is done based on where this thing is bolted to the wheel. So on what parts of this hub am I allowed to say these points are not going to be able to move in space, no matter what? These points are going to be fixed in space. And the answer is right where I'm bolting it to the wheel. So I'm going to click, instead of no method, I want to specifically hit related nodes, and I'm going to pick related nodes that are related to polygon faces. Specifically, which polygon faces? Well, the ones that are inside that are going to be directly affected by the bolt. So I'm going to click all 6 bolt holes, and now I have all of the points that are going to be fixed by the bolts selected. I'm going to click OK, and now all of those are shown in blue to be completely fixed in space. And now those guys are not going to be able to move when I start my simulation. The next thing I need to do is apply a load. So there are a lot of different great loading scenarios here. Usually the one we use is force, just because forces are what we easily apply. Accelerations are, be careful in using acceleration because we only use acceleration when the full weight of the force is in the model. So the only thing that's going to be applying the force, let's say it's a 5G load. If I was applying a 5G load to this part, as if the car was undergoing a 5G impact, well, that's not going to work if I use acceleration, because acceleration is going to think that the only mass I'm worried about is the mass of this hub. That's just not true. So we'd be using a force if I was going to do that. There's also a moment you can apply. There's torques, pressures, all sorts of stuff. Even hydrostatic pressure. That's kind of cool, to be honest. I've never really used that. Seems like more of like an educational thing, to be honest. But anywho, the load we're going to be using is the load of the wheel onto the middle of the hub. So if I bump the wheel upward very hard, it's going to be applying a large force right into there. And that force is going to be a bearing force, such that the force straight up is going to be of much greater magnitude than the forces off to the sides. And in fact, that force is going to decay sinusoidally until it reaches degrees 0 and 180. So the type of load I'm describing is a bearing load, so I'm going to go ahead and click on that. And the object I'm going to be selecting is this polygon face right here. That's the area to which I'm going to be applying this load. The vector, I'm going to go ahead and click. Once I clicked on that face, it automatically pulls up the specify vector dialog, and somewhere it should pull up this nice blue coordinate axis just a little ways away. Not this one, guys, not your global one, but a nice little blue one off to the side here. And I get to pick which direction is going to be the vector that I'm working with. And the vector that I'm working with is this guy, the z-axis. I'm going to be bumping it straight up. That's what I'm going to click, and sure enough, the golden arrow pointing straight upward appears. And I can switch the direction of that. Like, let's say it was a load in the other direction. I can click that arrow however many times I want, or I can just do this, and that also changes the direction. Yep, cool. And that is how I select the direction of my force vector. But I need 2 things to determine a force, both a to determine a vector, both a direction and a magnitude. So I define my magnitude right down here. Now I know my car is a 800-pound car with driver. So, but under even the worst possible bumping conditions, only a quarter of that is going to be on any given hub. So I can go ahead and say 800 divided by 4. But I also know that this is a 2G bump load, so I need to multiply that whole thing by 2. I also know that's not newtons, that's pounds. So 2 times 800 over 4, and it knows very nicely that it's going to calculate that expression for me and not make me do even very simple math. So I'm going to hit click OK. And there, sure enough, are my forces. As you can see, the ones in the middle are the biggest, and the ones off to the side are smaller. They deteriorate as they get further and further away from that big upward central one. Now that I have applied my bump load, and now that I've applied my constraints, I can finally go ahead and solve this thing. I'm going to let NX do a lot of differential equations, a lot of deformable bodies, and physical differential equations to figure out how this thing is going to deform and what stresses it is going to experience. So we have this nice solve button right up here. I click that, and I'm going to click OK, and now I just wait. Again, for you guys using a remote desktop connection or a laptop, this might take a while. The joke I always tell when I'm doing these is you wait for it to start like really going crazy, and then you pretend to type really fast. But I don't know. This is a small part, and I didn't use a super precise mesh, so it's already done. I'm going to go ahead and it'll be done. You'll notice when it says job finished right here. But what I usually do, to be honest, guys, is I usually pull up the task manager and wait and watch as this line jumps up as my RAM gets very, very consumed. And then when it goes back down, I know that it's done. But you couldn't see that because it was too fast. So go ahead and close all these dialog boxes that popped up. If you had any errors, maybe they'll appear. Maybe it'll tell you that you messed up. And honestly, if you have to deal with errors, until you get good at figuring them out, come find one of your leaders and we'll help you out. Well, let's see the results file. First thing I need to do is switch the tab over to this guy, the post-processing navigator. And this guy right now is kind of grayed out, but if I double-click on him, he turns into colors, and I can expand him, and I have all of these wonderful little displays right here. The one I'm worried about, and one we're usually worried about, is this one, the elemental stress display. And this is going to display my von Mises stress. So if I double-click on that, sure enough, there it appears. The question I get asked all the time is, wow, are you telling me that under 2 G's of bumping load, this is what our hub is going to look like? And the answer is, of course not. If it even started to look like this, it would fail, and it would crack, and it would break, and it would be awful. No. This is the displacement magnified, I think, tens of thousands of times. So this displacement is not real, but what is real is that the color gradient here symbolizes the amount of stress that each element is feeling. So as you can see, most of it is blue, which means it's at the lower end, but there are some parts of it, and they're in the parts we kind of expect because that's where the load is being applied the largest, that experience a lot of stress. And the highest stress we can see is 4.975 megapascals. And if I want to see exactly where I'm experiencing the most stress, I can go ahead and expand this post view, expand annotations, and click maximum. And that shows me exactly the node that is under the most stress here. Also, if I'm frustrated with this mesh look, I can go under post view, edit, edges and faces, and turn these both the edges and faces to none and click OK. And there go all of my edges and faces, and now I can just see a beautifully rainbowed out part. And it's still labeled with my element experiencing maximum stress. So oftentimes, guys, what we'll do is I'll look at the max stress and I'll say, okay, 4.975 megapascals. Well, I know I'm using aluminum, so I'm going to go ahead and pull up Chrome. I'm going to type in yield strength aluminum. And the yield strength of aluminum tensile yield strength is 276 megapascals, while the ultimate tensile strength is 310 megapascals. So this hub is obviously going to survive a 2G impact load. To be honest, guys, hubs aren't that hard to design, so it's pretty clear that that's exactly what would happen. Normally we look at this and say, oh my gosh, we have a factor of safety of like a lot. So I'm bad at math, sorry. So what we do is we go in and we identify, look at all this blue space. That blue means that I can shave off material and go back into my SolidWorks model, and I go back in and I can say, okay, I can thin this out, I can thin all of this out, I can thin all of this out, but what I can't thin out is right in here, this wall thickness. Let's say that this number was closer to the yield strength of 276. Maybe it's 250. Well, that's a little bit too close for comfort. So what that means is, guys, I need to go back in here and thicken this up, or do something that's going to alleviate the stress in this part of the hub. But we don't really have to do that in this case because we are way under the yield stress. For reference, guys, you probably already know this, but on this team we usually use a 1.4 factor of safety for yield stresses and a 2.0 factor of safety for ultimate tensile strength. And what that means, guys, is you take this maximum stress experience, this 4.795, and I go to a calculator and I can say, okay, 4.795, and I multiply that by my safety factor of 1.4, let's say. And that means that if the yield stress of the material is any less than this number here, I've got a problem and I need to redesign. And then I say, okay, 4.9, oops, I typed that wrong the first time, 975 times 2, my factor of safety for ultimate tensile strength, that's 9.95, and I can check the ultimate tensile strength, and I can say, okay, is the ultimate tensile strength any less than 9.95? If the answer is yes, then I have a problem. We like to be extra safe on this team, and those are good standards to abide by. Factors of safety of 1.4 for yield and 2.0 for ultimate. And that is the conclusion of our 3D FEA tutorial. We'll go into more detail with this later. Actually, I think we already have with older versions of NX also on this channel. But for the most part, especially for suspension components, this is all you guys are going to need. So, thank you very much for watching, and be pumped.